In this lecture I want to start discussing integration with multivariate functions, and we will start addressing double integrals first. So let's try to remind ourselves of what the theory of single variable calculus tells us. It tells us that if we want to integrate a function, we need to sum all the products in general from a to b of the values of the function times the differential along x. And in particular, if we want to visualize it, we have a function f of x. Here's the point x, here's the point x plus dx. So this very small line here is dx. And we multiply f of x at this point here times dx. So it's the area of this very small rectangle. Since we are summing all these areas, as dx goes to 0, these very small rectangles describe the entire area of the function between the points a and b. When we introduce another dimension, for instance, we have a surface right here in 3 dimensions, x, y, z, and this is the function f of x, y. We can visualize it as a surface here. So in here we have the point, for instance, f of xy. This is f of xy because this point has coordinates x and y, and then we move along z, but z is f of xy. Is the function that we are going to describe. In this case, we must do something similar to the one dimension case. Instead of summing areas of rectangles, we must sum
volumes of parallelepipeds.
So the sums that we have to carry out are of the kind f of xy times dx dy in this case, because dx dy is the area of this rectangle here, but we must multiply it by the height
of the parallelepiped, which is f of xy.
So we must integrate over these two differentials, and in general we need to carry out integration over x and integration over y. Sometimes people represent this by just putting an integration sign, just one, for sake of simplicity, but in general we have to perform two integrations. So sometimes you can also see this represented by two integral signs. And for instance, we will start with a very simple example and then we will dig deeper. For instance, we have a plane. If the plane is parallel to the x and y plane, so the x and y axis describe another plane. And if this is parallel to this plane, we can describe this plane by means of the equation z equals a constant. So this constant can be whatever number you want. For instance, if this constant is 0, then we get down to the xy plane. As we move along the z-axis, this constant increases. If you want to integrate this function, the very simple function f of xy equals constant, lambda. F of xy is equal to lambda. We want to integrate this function, for instance, from the point y1 to y2 and from x1 to x2. So this is the first point, then we have another point here. This is our grid here. Let me redraw this a little bit cleaner. I will get a parallelepiped. So this is the
volume of a parallelepiped.
What is the area of the rectangle here? That's just y2 minus y1 times x2 minus x1, and then we multiply by the height, but the height is just lambda because it's our function, but our function is just a constant, so it's just the value of the function itself, it's constant. We can obtain this result by performing an integration, a double integral of the function f of xy dx dy, and in general we put a symbol here as a subscript of the integration, which reminds us of the area of integration, of the domain of integration. That's better. The domain of integration in our case is just this one. It's the projection of the area on the x and y plane. So this is A, our A. This is the area over which we want to integrate. But overall we will get a volume. So we are going to sum areas times a height. That gives us a volume. In one dimension we add just a line, but we were multiplying a value times a distance, a length, so we would get an area in that case. In this case we get a volume. That's just the geometric interpretation. So this is equal to integration f of xy is just equal to lambda, so that's a constant, times dx and dy. We should insert here the boundary values of integration. Here the lower value is x1, and we're performing the integration all the way up to x2, and then we have in here y1 to y2. We perform the first integration. This is a constant, we can put it out of the integral sign, so this is integration from y1 to y2. The first integral is x, but we should evaluate it between x1 and x2. and then integrate over dy. This is a constant in y, so we have lambda times x from x1 to x2 times the integral of 1, but that's just y, and evaluated between y1 and y2. So this is equal to lambda times x2 minus x1 times y2 minus y1, and we get the same result as our intuition tells us.